visible, or say, let's should we say the useful, this is when I talk about PAR, measuring PAR levels with the PAR meter for the plant chambers and all that, what you're really measuring is between here. Now keep in mind this is watts per meter squared, where it's a little biased because a higher energy photon skews it. And remember, from photosynthetic standpoint, it doesn't matter if it's a little higher energy or not, because it can only ping and be, one photon is one photon. So I tend to express light in terms of micro-Einsteins, because micro-Einstein is a mole of photons, and it doesn't matter whether it's a higher energy photon or a lower energy photon, because from a photosynthetic standpoint, all photons are equal. If it's a little higher energy, it wastes it. Okay? We tend to do it this way because this is what heats up the world. Okay? The watts per meter squared, so this in this visible spectrum. You can see that a lot of energy is up there where it isn't going to be of use, and there's a lot of energy on the other side that is just simply too high intensity. What he's saying is taking these photons here and knock them back down. You can't upgrade. Okay? It's hard to upgrade. It's hard to take a lower energy one and make it there, but it's easier to take a high one and make it lower. And that's the goal. Yeah.
Just a more fundamental question. How much energy does the photosystem complex, whatever, actually use for that reduction at the end?
7%.
I guess like what energy, like equivalent of like a photon would be required for that? That's what I'm wondering.
Oh, well, the answer is in the Z-scheme. Okay, so you all remember your biology where then you have the one reaction center, and then it's got, and then it goes again. So functionally it needs 2 photons.
Okay.
The one hits, and then it starts to trickle down a little bit, and then it hits another one, and that gives it enough to get it to the point where it's actually enough energy to actually do the reduction of carbon dioxide. So the standard splitting of water, fixation, and so forth, functionally it needs 2 photons in order to do that. One reaction center 1, photosystem 1, and another one in photosystem 2. And that's how it works. But anyway, keep in mind that at one point in time, 90% of the lab was working on algae. Okay? A lot of algae work was going on. And so we've been playing with the algae thing for almost 20 years now in different forms of that. Right now we're doing mostly plant work. But there are certain aspects of this to try to contrast this to the recent proposals that we've written. Okay, one was if chlorophyll F, for example, is a chlorophyll that can actually capture energy out in this range here. Okay, and so there is a form of chlorophyll that was found in the ultra dense films of cyanobacteria, like in the hot springs and Yosemite, not Yosemite, Yellowstone, thank you. The amount of algae in those little tiny biofilms was equal to more algae than you would have in 20 fathoms of water in the sea. And so they realized that they would be severely light limited. And so they adapted and created a chlorophyll, because the ones that are stuck on the bottom don't have the impellers in a biofilm. They are stuck with trying to live with almost no light. Well, this light that's out here actually makes it doesn't get captured. And so if you're living down on the bottom of the biofilm, you're seeing all these photons, and oh, if I could only just use them. And so, not too surprisingly, biology accommodated and created chlorophyll D and chlorophyll F, which allow for capture that goes down into this. Now the question is, can we functionally add that back to a more modern quote-unquote algae like chlorella or one of the others, in that you could capture more photons? Now here's the problem. What his experiments are showing is that part of the problem is that when you have an optical density of 10 even, your light is so attenuated that most of it's sitting in the dark. And so by mixing it more, you're moving the dark ones to the light and the light ones to the dark, you can functionally make it more efficient to capture the actual electrons and so forth that are there. And so inherently, it's not just simply capturing it, because if these guys are exposed to light, they will waste it. If they have the ability to catch 10 hamburgers and they only need to eat one, okay, will they, this is a fundamental question that's been raised many, many times. Could you make algae less greedy? Because if I'm in the dark, I'm going to be like, okay, and I'm really, really hungry, okay, I'm going to be like, when I get to the light, I'm going to grab all 10 hamburgers, okay? And then I'm going to go, and then I'm going to say, like, oh, I could only eat one when I went back to the dark. I mean, what happened to the other 9 hamburgers? Well, I threw them away, okay? Could you actually convince them to share so that when they went out into the light, they only took 1 hamburger? Well, if the mixing is fast enough, they accept that. Like, hey, you know what? Okay, I don't have to grab 10, I'll only grab 3 hamburgers. Okay, that's literally what his thing is saying here. The problem is biology is not inherently communal. Okay, you take care of yourself. You grab that, and then you make. That's what I was saying about the adjustment. I may be like, I make my mitt only big enough for 3 hamburgers, then 2 hamburgers. I mean, I could be changing how much I actually grab. If we manipulate them genetically and give them an extra arm to catch, how are they going to use it? To be more greedy? Or not? And that's part of the fundamental question. Some people have said what we should be doing is manipulating their ability to grab hamburgers and change their actual light harvesting antenna, and therefore they can't. It's like, I can only catch 1 hamburger. Okay. And so you force them to be unselfish. Naturally, that would never happen. So you tell them, no, you're only allowed to, and therefore that extra 9 photons goes and somebody else gets to get them. And these are questions that people have been talking about in terms of how would one make that, including, this is the argument that, and the reason why that paper was published in Science when they discovered chlorophyll F. They just did a simple calculation. If we manage to plant our corn more dense, and we put chlorophyll F in there, and we captured more of the solar spectrum, how many more bushels of corn could we grow on a field? And did you read that paper in Science? Okay. That was one of the most recent. That was out of who was the cyanobacteria guy? Don Bryant. That was his paper, and he's our big cyan guy. And about 40% was the answer. If you could manage to take that enhanced ability to catch photons and truly use it effectively, you could plant your things more dense, and then as a result of that, actually increase the productivity of plants on the planet, because the argument being, well, true, normally plants aren't planted that dense. But genetic engineering, if it could give you the ability to catch more of the light, then you could do that. You could actually increase the productivity and so forth. So that was the inherent idea, and why it was published in Science, was this idea. If you could, in fact, genetically manipulate the solar spectrum that is useful for photosynthesis, you could dramatically change agriculture in terms of its overall productivity. Okay, we're done.